Hello, thank you everyone for joining us. My name is John Peters. I'm the product manager for elemental spectroscopy with Shimadzu Scientific Instruments. I'd like to thank everyone for joining, and CEM, Glass Expansion, and Robert Thomas for participating in this webinar today. I would like to discuss trace metals analysis in cannabis products, tips and tricks for the ICPMS-2030, how to optimize a method, hardware configurations, and how to best optimize maintenance issues. A little bit about Shimadzu. The corporate overview and philosophy is contributing to society through science and technology. The management principle is realizing our wishes for the well-being of both mankind and the earth. Shimadzu was established by Ginzo Shimadzu in 1875 in Kyoto, Japan. Currently, there are 3,000 employees in Japan and over 12,000 globally, with an annual revenue of $3.5 billion. In 2018, Shimadzu became the second largest instrument manufacturer in the world. Shimadzu in the United States was established as Shimadzu Scientific Instruments in 1975, a U.S. corporation to provide analytical solutions for laboratories in North America, Latin America, and the Caribbean nations. We have over 500 employees headquartered in Columbia, Maryland, with 10 regional offices providing sales, training, service, technical support, and marketing. Shimadzu Scientific Instruments offers a wide variety of analytical tools, including instruments for spectroscopy, chromatography, mass spectrometry, the life sciences, balances, consumables, the environmental markets, surface analysis, testing systems, thermal analysis, non-destructive testing, as well as training and support. Within that family of broad analytical tools and techniques is the elemental group, which includes X-ray, ICP, ICPMS, atomic absorption, and TOC. Relative detection limits for each technology can be seen on this slide, and it becomes apparent why the ICPMS is a preferred method for detecting the smallest amounts of mercury, lead, cadmium, and arsenic in a variety of matrices of benefit to human health. The ICPMS is used for cannabis analysis because it has the best detection limit of any technology available. Using a collision cell can reduce the amount of polyatomic interferences, and using assistant functions can reduce the amount of time required to develop a method. The ICPMS also has cost reduction features, including a mini torch, which allows for up to 40% less argon consumption, and an eco mode, which allows for 70% less argon consumption while in standby mode, as well as reduced electrical requirements. The collision cell can be used to reduce polyatomic interferences such as argon chloride, the summation of two present atoms in a solution that includes the argon gas and hydrochloric acid, which is used in some matrices to reduce carryover of mercury. Lab Solutions DB and CS for the ICPMS allows for 21 CFR Part 11 compliance in regulated labs, not just for the ICPMS, but for all of Shimadzu's instrumentation. One consideration when choosing sample preparation and processing techniques for a particular method is the type of sample that will be analyzed. Many samples do not require filtration. This would include MCT oils, edible oils, gummies, cheeses, etc. However, some materials containing plant materials will require filtration. This is because hemp, bamboo, cannabis flower, etc. is going to produce silicate particles even after digestion in the final solution. So these can be removed in a couple of different ways. One would be to centrifuge the tubes and then draw liquid off the top. This, however, is not entirely perfect because some particles are still present and it's time consuming. A second method would be to add some hydrofluoric acid to the solution to dissolve those silicate particles. This, however, presents some safety problems and wear on the glass. The best way is to filter these samples with a PTFE 0.45 micron syringe filter prior to running on the ICP. Note that the Guardian inline liquid filter is 120 microns and will not catch the very fine particles that could still damage the nebulizer and the efficiency of the aerosol. So one way to check this would be to take the nebulizer out of the spray chamber, put the probe into a water bath, and then turn on the peristaltic pump and the nebulizer gas manually, and observe the aerosol coming out of the end of the nebulizer. It should be symmetrical. It should have an even uptake rate close to 0.6 milliliters per minute. It should have fine particles, very fine mist, and it shouldn't spit like inconsistent rate of spray. So all of this can be observed by looking at the aerosol coming out of the end of the nebulizer manually. And if there's a problem with any of those components and the type of aerosol coming off, the nebulizer can be cleaned and back flushed and then returned to proper working order. Another consideration when planning an ICPMS method for cannabis analysis on ICPMS is the matrix of the solutions which will be analyzed by the instrument. Dilution of the acids coming off of the digester is recommended to be less than or equal to 5% nitric acid. So this would be 5 milliliters of acid diluted to 100, the acid being a 70% stock solution. Same with 37% HCl. We would consider that if you put 1 milliliter into 100 milliliters, we would call that 1% by volume. So the reason for dilution to this level is severalfold. Reducing the viscosity of the sample matrix improves the efficiency of the aerosol so that more of the particles are fine coming off of the end of the nebulizer, and thus the signal is enhanced. This improves the signal to noise ratio and improves then the detection limits of the method. Another advantage is to reduce the maintenance costs. Running higher acid, particularly hydrochloric acid, into the ICPMS eventually erodes the cones and the O-rings around the shutter. It also wears out the detector more quickly. So improved maintenance costs and longevity of the instrument is improved by lowering the acid content and having a higher dilution. It's also recommended to have the same matrix for samples in sequence, so that if you're running a 1% nitric acid as a CV, you also have a 1% nitric acid in your samples next to it. This way, the different acid contents are not mixing together in between samples and creating density problems and fluctuations in the internal standard signals. This can help with consistency and reduce the number of blanks that need to be run in between samples. Carryover considerations should be of paramount importance in the development of an ICPMS method for cannabis. Mercury in particular is difficult because it's sticky and prone to carryover problems. A couple of different techniques have been utilized successfully to reduce mercury carryover. One is 0.5% hydrochloric acid in the matrix and the rinse solution. The advantage of this is ease of use, the cost. However, the disadvantage is twofold. One, it's corrosive and it tends to wear out the components of the ICPMS more quickly. For example, the cones and the O-rings around the shutter, for example. Also, there is an interference with chlorine, chlorine being 35 and argon being 40. The two have the same mass as arsenic, 75. So polyatomic interferences become problematic when the hydrochloric acid is present in solution. Another technique has been to add 1 part per million gold to all of the matrices and the rinse solutions. The disadvantage of this is that it's a little bit costly and there are possible isobaric interferences as well. The best one that we've found is to add 0.1 to 0.5% L-cysteine into both the sample matrices and the rinse solution. This takes care of the mercury carryover without the isobaric or polyatomic interferences and without wearing out the components of the ICPMS. To reduce carryover, additionally, a dual rinse station can be employed as seen in the photo. This means that there can be a different rinse solution for each of the two stations and better carryover washout. You can also change the amount of time and the speed at which rinse solution is uptaken. Also, a rapid sample introduction hardware component can be added on the front end, similar to the glass expansion Niagara. Hardware recommendations for ICPMS analysis of cannabis include using nickel cones over copper cones. Nickel will last longer in acid environments and are cost effective. Platinum cones are available at a higher cost, but are only required when using any amount of sulfuric acid in the matrix, which is uncommon for cannabis. Gold-plated RF coils are recommended also due to the longevity of the component and cost effectiveness. An inline filter for the liquid and gas are recommended to protect the instrument, although filtering samples with silicates coming out of the digester is also recommended. A power conditioner can regulate the voltage going into the instrument and thus the baseline, which will improve the detection limits of the instrument as well and protect the equipment. Proper ventilation can also improve the detection limit by ensuring stability of the plasma and reducing heat buildup inside the instrument. Maintenance and tuning recommendations are available for download. The ICPMS is a robust and reliable instrument when used according to the maintenance and tuning recommendations and guidelines published. A sample front end can also improve the longevity of the instrument and throughput by ensuring that less sample is required and less rinse solution in between samples. I'll allow my colleagues at Glass Expansion to explain further. The experimental conditions and hardware configuration for this setup was standard for Shimadzu's ICPMS-2030. The method was developed to target elements arsenic, cadmium, mercury, and lead, as required by California and all other states for cannabis regulations. The CEM digested samples were diluted to contain 4.5% nitric acid and 0.5% hydrochloric acid before measurement. Digested and diluted samples were analyzed with the ICPMS 2030 using a Niagara CM rapid rinse sample introduction systems on the front end. The standard ICPMS-2030 sample introduction system was also employed: coaxial gas nebulizer, cyclone, spray chamber, mini torch, nickel sampling cones, and nickel skimmer cones. The internal standards were scandium, indium, and bismuth, and the internal standard automatic addition kit was employed. The operating conditions for this experiment are listed here. Here we see some of the results for arsenic, cadmium, mercury, and lead, including detection limits in the parts per trillion level and R-squared values of 3 nines or higher. Consistent calibration curves in the range of the desired detections for each element is always required for a method. And here we see very good linearity for each of the elements selected. Here we see spike recovery data and precision data for a variety of different sample matrices, including hard candy, sugary material, a granola bar, a suspension lotion, a soft candy, froggy, and hemp flour as well. So we see for all 4 of the elements that the spike recoveries are within 10%, and the RSDs are all very good, except in a couple of cases for arsenic where the collision cell is employed in order to reduce the polyatomic interference from argon chloride. Additional spike recovery and RSD data for the 4 elements are included here. MCT oil, cheese, hemp oil, beef jerky, peanut butter, and concentrated CBD oil were all digested successfully and produced excellent reproducibility, accuracy, precision, and spike recovery data. So for the non-scientist, the most interesting part of this study is how much of these harmful elements are actually in the materials that are available to us as a consumer. All of these materials were purchased at the grocery store or in some retail outlet. So knowing the content of arsenic, cadmium, mercury, and lead in each is of great interest to the consumer, of course. It's the reason we're doing this. So this table shows the results as indicated by our method. Now, the non-detect data is less than the detection limit of the method as calculated, which was 8.2 parts per trillion arsenic, 1.3 parts per trillion cadmium, 2.3 parts per trillion mercury, and 0.3 parts per trillion lead. I would like to thank everyone for attending the webinar today, and for my colleagues for their presentations as well. If there are any questions, please stay around after the webinar and we will answer them. Thank you very much.